Hello everyone. Welcome to lecture number 4 on the topic Concepts of Working Stress Method in the Design of RCC Structures. In this lecture, we are going to study the working stress method, which is one of the classical methods of RCC design. So although modern codes mainly adopts a limit state method, the working stress method is very important because it explains the basic elastic behavior of RCC members. Also, it forms a foundation for understanding the stress distribution. In this lecture, we will focus on the conceptual aspects of the working stress method before moving to detailed numerical analysis and design in later lectures. Before applying elastic theory to reinforced concrete, we must understand an important concept called the modular ratio. So reinforced concrete is a composite material consisting of concrete as well as steel. The concrete and steel have different elastic properties, particularly different moduli of elasticity. Since the working stress method is based on elastic theory, we cannot directly analyze concrete and steel together unless we bring them to a common material basis. This is done using the modular ratio, which is denoted by small m. The modular ratio is defined as E is equal to ES by EC, where ES is the modulus of elasticity of steel and EC is the modulus of elasticity of concrete. So as per IS standard, ES will be assumed as 2 into 10 power 5 Newton per mm square. And EC, the Young's modulus or the modulus of elasticity of concrete, will be assumed to be 5700 root FCK. And based on the latest revision, this has been revised as 5000 root FCK. So using the modular ratio, the steel area is transformed into an equivalent concrete area, allowing us to analyze the section as an equivalent concrete section. As per IS code recommendations, the modular ratio is generally taken as M is equal to 280 divided by 3 sigma CBC, where sigma CBC is the permissible compressive strength in concrete under bending. The concept of modular ratio is fundamental in determining the stress distribution, neutral axis depth, as well as the moment of resistance. The working stress method is based on the following fundamental assumptions. First, the plane sections remain plane before and after bending. This implies that the strain distribution across the depth is linear. Second, all tensile stresses are carried by steel reinforcement and concrete is assumed to resist no tension. The third, the stress-strain relationship of concrete and steel is linear under working loads, indicating the elastic behavior. Finally, there is a perfect bond between steel and concrete, and hence there will not be any slip which will be occurs between them. These assumptions make it possible to apply simple elastic theory to RCC design. So below the table shows for different grade of concrete the values of sigma CBC as well as modular ratio. So in general, basically this sigma CBC will be calculated as approximately 1/3 of the characteristic compressive strength of concrete. For example, you can see M15 grade concrete has a characteristic compressive strength of 15 Newton per mm square. So 15 divided by 3, you will be getting 5 Newton per mm square, which represents the sigma CBC value. Regarding modular ratio, once sigma CBC is known, as per the assumption, M can be calculated as 280 divided by 3 sigma CBC. With this value, the modular ratio for different grades of concrete can be computed. And these assumptions make it possible to apply simple elastic theory to RCC design. Now, coming on to the singly reinforced section. What is singly reinforced section? First of all, a singly reinforced section is a reinforced concrete section in which a reinforcement is provided only on the tension side, while the compression side is resisted entirely by concrete. Since concrete is weak in tension, steel reinforcement is placed in the tension zone to resist tensile stresses, whereas no steel is provided on the compression side in a singly reinforced section. Singly reinforced sections are generally used when the bending moment is moderate, the depth of the section is sufficient to take care of the applied loads, and there is no reversal of bending. So most RCC beams designed under normal conditions are singly reinforced and under reinforced, which ensures ductile behavior and gives warning before failure. Because of their simplicity and economy, singly reinforced sections are commonly adopted in RCC design. Let us now examine the stress and strain distribution in a singly reinforced RCC beam subjected to bending. When a reinforced concrete beam is subjected to bending, stresses are developed across its depth. Based on the assumption that plane sections remain plane, the strain distribution across the section is linear. That's what you can see the strain diagram. This actual variation of stress across the depth of the section is represented by what we call the stress diagram. This one. In a singly reinforced section, the upper portion of the beam is under compression and the lower portion is under tension. So the concrete resists compression while steel reinforcement resists tension. The concrete stress varies linearly from 0 at the neutral axis to a maximum value of sigma CBC at the extreme compression fiber. Concrete in the tension zone is neglected and the entire tensile force is carried by the steel, which is subjected to a tensile stress of sigma EST. That's what has been given here. Now, for ease of calculation, this actual stress diagram is simplified into what is known as the equivalent stress diagram. This simplification makes it easier to calculate the compressive force in concrete as well as the tensile force in steel and ultimately the moment of resistance. So the simple changes, instead of having sigma ST, the equivalent concrete area is being calculated by using the relationship sigma ST by M, where M is the modular ratio. Now, calculation of the neutral axis depth. We will have two different cases are available using which the neutral axis depth can be calculated. Number one is if the cross section details are known as well as the extreme stresses in both the materials are given in the sense, we can go by this method. In this case, the beam dimensions, the permissible stresses as well as the modular ratio are given. So we can use this stress distribution diagram, the equivalent stress distribution diagram, using which we'll apply the similar triangle approach. Based on that one, we can derive the formula as sigma CBC divided by sigma ST by M, which will be equal to x divided by d minus Ex, where x is the depth of neutral axis. So using which the x can be computed. So to find the area of the steel, AST, equate the total compressive force to the total tensile force. Now, Coming on to the total compressive force C, which will be computed as the product of area and the average compressive stress. So which will be calculated as B into X, that is a concrete area, and regarding the average compressive stress, it varies from 0 to a maximum of sigma CBC. So that is why 0 plus sigma CBC divided by 2, you will be getting the value as Bx sigma CBC by 2. This is the total compressive force acting on this section. Now T, the total tensile force acting on the section, will be computed by multiplying the area of the steel with the tensile stress developed in this section. Since we already taken the equivalent stress distribution, so we'll be using the formula AST into sigma ST, where AST is the area of the tensile steel and sigma ST is the maximum permissible tensile stress in steel. So equating these two, we'll be getting the relationship Bx sigma CBC by 2, which will be equal to AST into sigma EST. So using this relationship, AST, that is the area of the steel, can be computed. So once if the area of the steel is known, we can also find the percentage of the steel, because IS has specified some minimum and maximum percentage of the steel adopted for different sections. So in that case, we are supposed to find the percentage of the steel also. So how to compute this one is PT, percentage of the steel, will be denoted as PT, which will be calculated as the ratio of the area of the tension steel provided to the effective cross-sectional area, that is B into effective depth, into 100 in order to get it in terms of percentage. So in addition to this one, while moving on with the design problems, we may require to find some design constants. Starts off with the depth of critical neutral axis. So this formula has been modified in order to get a relationship as 1 divided by 1 plus sigma ST by M into sigma CBC into D, using which the depth of the critical neutral axis can be calculated. This is applicable for a balanced section, theoretical case, which will be taken as a reference one. Then J, small j represents the lever arm factor, whereas Z represents the lever arm value itself. So this lever arm factor can be calculated by using the relationship 1 minus XF by 3, where XF is the critical depth of neutral axis factor. How to calculate this one is whatever the value which is available within the square bracket of this depth of critical neutral axis formula, which will represent the factor for calculating the critical depth of neutral axis. In addition, the design constant Q can be calculated with the relationship half into sigma CBC into X into J. So these are the design constants which we are supposed to know while moving on to the design numericals. Now let us move on to the second case. If the cross-section details are known as well as the area of the steel is known rather than the permissible stresses, if the area of the steel is known, we need to find the depth of neutral axis. First, let us consider the compression side, in which we will be using the relationship moment of area of the compression side to the moment of area of the tension side. So we will be equating these two in order to get the relationship for finding out the depth of neutral axis. In a singly reinforced RCC section, the compression zone consists only of concrete above the neutral axis at this area. The depth of the compression zone is equal to the neutral axis depth X. The area of the concrete in compression will be calculated as B into X. So this is the B and the depth is X up to the neutral axis. The centroid of this rectangular area lies at a distance of half of this one. Since it is a rectangular area, its centroidal axis will be lying half of its total depth, that is x by 2 from the neutral axis. Therefore, the moment of area of the compression side above the neutral axis is being calculated as Bx into x by 2, which will be equal to Bx square by 2. Now let us consider the tension side. On the tension side, concrete is neglected and only steel reinforcement is considered. However, since steel and concrete have different elastic properties, the steel area is converted into equivalent concrete area using the equivalent stress distribution, using the modular ratio M. So equivalent concrete area of the steel will be M into AST. The steel is located at an effective depth D from the top. That is, the steel is located here, which is at a distance of small d from the topmost portion of the beam. So the distance of the steel from the neutral axis is total is d minus Cx. This is the value should be taken. So therefore, the moment of area of the tension side above the neutral axis is M into AST into d minus X. So equating these two according to the condition of equilibrium of moments of areas above the neutral axis, we'll get the relationship as bx square by 2 will be equal to M into AST into d minus X. Solving this equation, which will give the depth of neutral axis X. So this method is known as the moment of area method and is widely used in analysis problems under the working stress method. And this method is particularly useful in analysis problems where reinforcement details are given. So when an RCC beam is subjected to bending due to external loads, internal stresses are developed in concrete and steel. So these internal stresses produce an internal resisting moment which opposes the external bending moment. This internal resisting moment is known as the moment of resistance. In simple words, the moment of resistance is the maximum bending moment that a beam section can safely resist under the working stress method without exceeding the permissible stresses in concrete and steel. In the working stress method, the moment of resistance is calculated by considering the compressive force in concrete and the tensile force in steel. In addition, the lever arm between these two forces will be taken into account. So the general expression is moment of resistance will be equal to the internal force, either compression or tension, into lever arm. That is what has been given. Either tension T or C into the distance between the two forces Z, which will be denoted as Z. Now, the value of the moment of resistance depends on the type of RCC section. They are under reinforced section, over reinforced section and balanced section. So in under reinforced section, steel reaches its permissible stress first, while concrete stress is still within its limits. So the moment of resistance here in this case is governed by the tensile force in steel. Next, the over reinforced section. So here the concrete reaches its permissible compressive stress first before steel reaches its allowable stress. So the moment of resistance in this case is governed by the compressive force in concrete. Whereas in a balanced section, both the steel and concrete reaches their permissible stress simultaneously. So this represents the limiting conditions between under reinforced and over reinforced section. In case of under reinforced section, the moment of resistance can be computed by multiplying the total tensile force with the lever arm distance. In case of over reinforced section, the moment of resistance will be computed with the product of total compressive force with the lever arm distance. In case of balanced section, this can be calculated since it is an benchmark case. This can be either calculated as an under reinforced section or it can be calculated considering it as an over reinforced section. So both the formulas can be applicable in case of a balanced section. So that's the moment of resistance represents the safe bending capacity of the section as per elastic theory. So this concept is extremely important because in design we ensure that the moment of resistance of the section is always greater than the maximum bending moment caused by external loads. In the next stage, we will apply this concept to numerical problems and beam design using the working stress method. Thank you.